Okay, so welcome back, everyone. I have had some questions about really trying to understand the difference between a microstate and its link and a quantum state was the question. And so, really, with this, we're going to try to further explain what is a microstate and how does that relate to the quantum mechanics of the system. And so, really, what we're going to look at is counting microstates, the bigger picture. Okay, so what is a microstate? So, as we think about molecules and a whole system of molecules, this can get very vague and hard to imagine in our heads. So, what we tend to do is go to some sort of thought experiment that we understand. So let's think that we have two six-sided dice. So like the regular dice that we have in Yahtzee. And we throw the dice. We roll them. How many different combinations of dice can we get? It turns out that more information is needed because we need to know if we can distinguish the two dice. In other words, are both dice white or are the dice two different colors? So what we're really thinking about is in this picture we have a 6 and we have a 5. In the other arrangement we have a 5 and a 6. And our question really is, are these different? And depending upon the game that uses dice that you might be using, you might just be looking at the total and it's an 11, which means that these are not different. But in other games, that having a red dice as a 5 and a white dice as 6 means something different than the other way around. So if the dice are the same color, then these two combinations are the same. So if the dice are not the same color, our question becomes, are the arrangements still the same? So in this one, we have a blue 6 and a red 5. And in arrangement 2, we have a blue 5 and a red 6. So the opposite. So there's still, are these different is our question. So they still both add up to 11, but they add up to 11 with different colors. So in our 2 white dice example, these are said to be indistinguishable. In our different colors die, these are distinguishable. Okay, great. We see this with dice. What about molecules? So this is where things start getting tricky because we have to really define what we are looking at and what we know about the system in order to be able to identify if our individual molecules are distinguishable or not. So most of our indistinguishable species are whenever we're thinking about, say, a beaker of water, and we're going to treat all of those water molecules the same. A collection of electrons, these are indistinguishable. Anything where we are saying that all of the molecules in the system are going to behave the same means that they're indistinguishable. But there are cases, even in chemistry, that we talk about distinguishable particles. So an example would be a system that is a mixture of molecules, say ethanol and water, for example. In that, we would be able to distinguish between the ethanol molecules and the water molecules. These are different, and we could say, based upon properties, that we can distinguish between the two. A system composed of different isotopes when we can watch the mass. So if we have a mixture of helium-2 and helium-3, and we are doing something where, say, we're doing mass spec and we're monitoring the composition of our sample based upon the amount of each of these isotopes, then we are distinguishing between these species. So whether or not a system has distinguishable or indistinguishable particles really comes into play when we start counting these microstates. But this, in reality, we have to really know what we're studying to be able to figure out if we actually can distinguish the particles in the system. So if we are saying that our molecules are identical, so we've got that beaker of water and we have identical particles. In order to do this, we are making some approximations because two particles are said to be identical if all the properties are the same. This means that they have identical energies: translational, rotational, vibrational, and electronic. And as well as they have the same isotopes, they have the same nuclear spins, everything about them is identical. Being able to say that our molecules are identical is nearly impossible. There are a lot of properties of molecules, and we don't know all of them, and we're rarely measuring all of them. And so, in order to say that we have identical particles, we really are making some approximations. Okay, so now let's get into some examples on counting microstates. So, if I have one 6-sided dice, how many microstates are there in the system? Another way of asking this question is, how many possible answers are there? Well, it's a 6-sided dice. One side is a 4, one side's a 5. So for this, we have 6 possible microstates. Because a microstate is a possible answer, a possible existence of this dice. So let's make it a little more complicated. I now have 2 identical 6-sided dice. How many microstates are there for this system? Well, dice number 1 has 6 microstates. Dice number 2 has 6 microstates. And if we know any sort of combinatorics or probability theory, the omega number of microstates for this system is going to be 6 times 6, or 36 microstates. Okay, now let's think about this as molecules. So we have 10 indistinguishable molecules that can exist in 3 different energy states. Each energy state can hold 1 molecule. So instead of dice, we're going to switch to cards, the other form of probability theory. So really what we're saying is that we have 10 cards. We're looking at the back of those cards, and you are going to choose 3. So to do this, probability theory gives us this formula. Now, if you don't know what this exclamation point is, this is a factorial. And I'm going to show you what it means in a minute. Okay, so for this, n is going to be our number of cards or a number of molecules. So we have 10 factorial divided by n1 is going to be how many cards we're choosing or how many energy states that there are. And it's 3 factorial. So this means that we have, factorial means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all divided by, and I'm not going to write all this out, 3 factorial times 7 factorial. And if I do this math, I get that there are 120 different combinations for this condition. Okay, but Dr. Muir, this can get much more complicated. Is that the only formula that we use? You're right, it can get more complicated. So let's look at the next one. Okay, so a more complicated situation is if I have 10 molecules that can exist in 3 different energy states. Energy state 1 can hold 3 molecules. Energy state 2 can hold 2 molecules. Energy state 3 can hold 1 molecule. So I have my energy state. We said 1 can hold 3 molecules, 2 can hold 2 molecules, and 3 can hold 1 molecule. And the question is, if I have 10 molecules to start with, how many different ways can I put those 10 molecules into these 3 energy states? This is very similar to taking a deck of 10 indistinguishable cards, first choosing 3, then choosing 2, and then choosing 1. So combinatorics tells us that this is the formula that we use. Don't worry, you do not have to identify what formula to use in which situation. This pi, this is the product operator. This is just like the summation operator. Remember that big sigma? This just means that for all of the things, we are going to multiply them together instead of adding them together. So to do this out, you would do our 10 cards divided by our Ni is going to be our state. So state 1 takes 3. State 2 takes 2. State 3 takes 1. And this gives me 302,400 different combinations. So this should give you an idea that the numbers of omega that we're working with are really large, because this was 10 molecules. Think about how large a state actually tends to be. Okay, so you're probably thinking this seems really complicated. It is. Counting microstates is really hard. We have to know a lot about the system that we're studying. And in order to determine our entropy with S equals K log omega, we're going to have to know if our particles in our system are distinguishable or indistinguishable. We'll have to know the number of possible energy levels or really any other condition that can exist. And we're going to have to know the number of molecules that can have each energy or condition. Now, you are not expected to calculate omega for any real system because you saw how, depending upon the system that we were looking at, the way of calculating omega is different because we really have to understand probability theory and combinatorics to really say what are we actually counting. There is math to do that. People do this. We're not going to do it because we don't know enough about our system to be able to do it. We aren't working with cards or dice. We're working with molecules, and we're working with our molecules, we don't really have all the information all the time, because in order to get that information, we either have to kind of arbitrarily created, that we have to make decisions about it, or we have to measure it. And making decisions and choosing things is opens ourselves up for assumptions and errors in our models, and measuring it is really hard. Okay? So I hope this kind of started to help merge together what is a microstate and what is a state of the molecule. And helped answer some questions about what is a microstate.